So let's go ahead and look at another example of a proof that uses cases. So here we're asked to show that for integers m and n of opposite parity, and opposite parity just means one of them is even and one is odd. So that's what it means to have opposite parity. We want to show that m plus n is odd. So how could we split this into different cases? Well, let's see here. M and n are of opposite parity, so one is even and the other is odd. So a convenient way for me to split this up is, well, let's consider the case where m is even and n is odd, and then consider the case where m is odd and n is even. And those will be my two cases. So say m is even and n is odd. We have already seen lots of proofs like this. We already know the definition of even and odd, so let's go ahead and go through this pretty quickly. If m is even, that means I can write m as 2 times some other integer. And if n is odd, that means I can write it in the following way. There exists some other number some other integer, t2, such that n equals 2 times t2 plus 1. That's what it means to be odd. And so I want to show that m plus n is odd. So I'm using a direct proof technique right here. I've assumed m is even and n is odd. Now I just want to show that their sum is odd. Let's see what m plus n equals. Well, I can just plug in 2t1 for m. And I can plug in this expression for n. And then you can see we can factor out a 2 from the first two terms. And there we go. We see that this here is indeed an odd number. It's 2 times some integer plus 1. So I'm skipping over a little bit of details here just because we've seen proofs like this quite a few times in the past. But that was just case 1, where m is even and n is odd. Let's consider the other case. So here, I flipped it. M is now odd and n is even. Then, well, we're just basically going to do the same thing. So we have m is odd. That means I can write it as 2 times some other integer plus 1. And n being even means that I can write it as 2 times some other integer. And again, now all we have to do is consider m plus n and see whether or not it's even or odd. Plugging in 2t plus 1, 2t1 plus 1 for m. Plugging in this for n. I see that I have an expression that looks suspiciously similar to that up there. I can rearrange it and factor out a 2. And there we go. M plus n is indeed odd. It's 2 times some integer plus 1. Is odd. And I have finished my proof by cases. And you might be asking yourself, well, hang on, these two cases look really suspiciously similar to each other, right? Basically, I'm doing the exact same thing. All I've done is, in case 2, basically switched the roles of m and n. Here, m was even. In case 2, I switched it to n is even. Here n was odd, and in the case 2 I switched it to m is odd. This is actually the heart behind the term without loss of generality. And that was the whole reason actually why I wanted to give you this example of a proof by cases, was to motivate this term without loss of generality. So in the next video, we are going to consider without loss of generality in more detail.